thanks. Good. So let's see. So last time we kind of finished finally on time. One sort of method which you could, in some sense, consider to be a one-dimensional localization, which is balanced, but it's for a very specific balancing function on this mean curvature functional. So it only really works if you're trying to study. If you have to start with an isoparametric minimizer to make this method work. Okay, so if you want to develop more general methods that will allow you to have an F-balancing for more general situations, then you need to do something else. Okay, and of course, I'm not presenting this in any chronological order or something like that. Just in fact, now perhaps we are going to introduce the oldest kind of method available for localization. Okay, this is the one-dimensional localization. Via bisection. Okay. So this method was introduced, was first used, as far as I know, by Payne and Weinberger. In 1960, to study. So these are guys in various things, but in particular PDE. And they wanted to study the classical Neumann problem, first eigenvalue problem for the Laplacian. So we want to solve this equation for the first eigenvalue, non-trivial eigenvalue, with Neumann boundary conditions on the boundary. Okay, you want to get estimates for lambda 1 for the first non-trivial eigenvalue. Okay, and you want to do this in general. I mean, you need some information, so on convex K. So they introduced kind of a baby version of this method. I mean, all the ideas are kind of there to get a sharp estimate on lambda 1 as a function of, let's say, the diameter of K. Okay, and later this method was used. Well, much later, this was used by Gromov, as mentioned by Gromov and Emanuel Milman in the 80s. To do various things, for instance, to obtain to recover the sharp isoparametric inequality on the sphere, and also to study concentration properties of uniformly convex sets, whatever that means. Okay, so there kind of the method evolved even more. As we saw, you can actually get not just one-dimensional needles, but higher dimensional ones. But I'm only talking about one-dimensional needles in this kind of mini course for various reasons. First of all, they have the property that they will inherit the CD rho n, which everybody likes here in this audience, in this community. Higher dimensional needles will not necessarily inherit that. And second of all, this notion of a needle supported on a geodesic, we'll talk about this tomorrow, is available on a general manifold, whereas two-dimensional needles already, that would mean something like totally geodesic surface does not necessarily appear on manifolds. So that's why we're kind of restricting to 1D. Okay. Anyway, this was a big step was done by Kahn and Lovas. So somehow all of these authors kind of maybe rediscovered this method independently. Kahn and Lovas and Shimonovitz. I know the trick already. Okay. I learn. You learn, hopefully, and I learn. Okay. Kahn and Lovas and Shimonovitch in the 90s. So these are, well, Lovas is, of course, super famous, but the others are quite famous as well, but mostly motivated by problems in computer science, actually. They applied this method to study various isoparametric and other properties of convex sets. And this method was used by subsequently in the convexity community following their work. So used by many, many people, primarily actually by Sergei Bobkov. Okay. So really it slipped to many other communities, probability community and so on. We heard about some other names, I mean, yeah, Guédon, Ferdolizzi, I mean, many people use it, including myself, in various works. It's a very useful method, as I think the first 2 lectures, I hope, convince you. And subsequently, actually, this was used by other, or modified and refined by various other famous analysts like Nazarov, Sodin-Volberg, and Carberry and Wright. For instance, you can use this method. So besides the application that I mentioned, which kind of maybe reflect my interest and maybe somehow are tangential to some of your interests, but you can use this method to not just do sublevels, isoperimetric inequalities, but also study something about distribution of zeros of analytic functions. This was in the work of Nazarov, Sodin, Volberg, and so on. So I hope that you're already convinced by now that it's kind of useful. And anyway, the problem with this method that I'm going to present, it's restricted to Rn with some extensions as done here. You can extend it to some maybe special manifolds like Sn, but basically there are significant restrictions on the bisection method. Okay, we'll see why. So here's a theorem. You won't find this kind of in the literature this way. Try to explain why, but let me attribute this as kind of to Emanuel Milman, to Kanalova Simonovic. Okay, it says the following. So assume that we have a measure. Let's say probability measure, but it's not very important. Let's say probability. I mean finite mass. Again, not important. Let's assume that psi is continuous. Again, in applications, it's not terribly important. At the end, we want to prove inequalities. So if you know this for continuous functions, according to the direction of equality by approximation, you can get semi-continuous, either lower or upper, according to kind of the inequality that you're after. So a posteriori, you always kind of relax this to semi-continuity. Then if you have a function, L1, which integrates to 0, right, that's the basic balancing condition, then indeed there exists an F balanced 1D localization. So remind you for the millionth time, what does that mean? It means that you can write mu, you can disintegrate mu into these one-dimensional needles. So what does that mean? So that, well, first of all, the balancing condition, f d mu alpha is equal to 0 for nu almost every alpha. Okay, so that's the balancing condition for every needle. Every needle, mu alpha, is supported, well, okay, geodesics on Rn are easy, supported on an interval. Let's say L alpha, some interval in Rn. And thirdly, then that's part of the crucial information that you get here. This is kind of the analog of CD rho n gets inherited. It's precisely the analog. I mean, mu alpha is equal to, so it has a density with respect to the Lebesgue measure on this interval. And the density is equal to, okay, the original density that we had times J, which of course stands for Jacobian. We kind of already know where this Jacobian comes from the analysis that we already did, with the property that this Jacobian to the power 1 over n minus 1 is concave on its convex support. Okay. In other words, what does this mean? It means that actually this interval, well, or at least it's the support here. So the support of this J equipped with the usual, okay, we're in dimension 1 with the only distance that we have, and JT. Well, this satisfies in our language CD0M. Right, it's exactly what that means. Okay, and in particular, maybe I'll continue here. In particular, if the original space was CD rho n, again, n in this range that we saw, then This means that all of these one-dimensional guys, mu alpha, inherent CD rho n. It's exactly the same Cauchy-Schwarz argument that we saw yesterday, okay? Because if if j, we saw that if you can control the logarithmic Hessian of this guy, and you can control the logarithmic Hessian of this guy, this is exactly this data, saying that our density, our measure, our space is CD rho n, says that exactly you can control the logarithmic Hessian of psi, and here this information tells us that we control the logarithmic Hessian of j. Therefore, by Cauchy-Schwarz, if capital N is in that range, you can control the logarithmic Hessian of the product. Okay, so I mean, there's nothing new here. It's exactly what we did yesterday, but really the information is here. So the density of the needle is original density times this factor. Okay, good. So let me give. So finally, I mean, let me give you the idea of the proof. And that's kind of the role of these talks today and tomorrow, and to continue kind of giving you ideas of how to construct such. And now you see F is finally general. This is the first time we see a method, but it only is only going to work in Rn. So the idea of first ingredient is a very easy bisection lemma. Okay, it says something very easy. So assume that you have an absolutely continuous measure. You have a balanced function. Okay, and you have some point in Rn, and you have some S1 inside the tangent space here. So anyway, you take a point in Rn and you draw a circle, okay, an S1. Okay, then for any S1 here that you can draw, there exists a point, and this is S1, so that, I'll write what I mean, H plus theta is equal to H minus theta is equal to 0, where what is H plus and H minus? So this is my point P, right? I'm in Rn. I have someone gives me this S1. I can find, so theta is a direction here, and H is just H theta would be the hyperplane orthogonal to theta, and H plus would be this guy, and H minus would be the other guy, right? Okay, so just the half plane in the half plane in the plus and negative direction or perpendicular to theta. Okay, so I mean anyone can prove this. Basically, Yashar in his talk indeed mentioned that if you have more than kind of one condition which you want to bisect, then you need to use Borsuk-Ulam theorem. Okay, so this is where the kind of topological, very non-trivial topological method. But here in this case, we just have one. We're going to get one-dimensional needles. We just have one kind of condition, balancing condition that we want to bisect. So then the proof is just trivial. You just have an S1. You don't have a higher dimensional sphere. So the proof is trivial because if we look at the function theta going to, let's call this theta theta, which is the integral of, let's say, H plus theta, f d mu. Okay, so what do we know about this function? It's continuous because our measure was absolutely continuous. Right, so this function is continuous, and it's odd. It's odd because if I add b theta plus b minus theta, of course the measure of the of exactly what's going on this hyperplane is 0. The measure is absolutely continuous, so I just get the integral of f on the full space, which was assumed to be 0. So this is why it's odd, right? So if you have a continuous function which is odd, there is going to be some theta which is going to be equal to 0 because if it were positive somewhere on the antipodal point, it would be negative, and by continuity there should be a point in the middle where it's 0. Okay, so QED, there exists theta naught, so that repeat beta naught is equal to 0. So, you know, this is kind of silly Borsak Ulam in dimension 1. Okay, so this is the basic idea. So now how do we continue from here? Okay, so what's the idea? Step 2. Okay, the idea now is, okay, you give me a point and you give me an S1 on that point. I have my space Rn. I'm going to find a hyperplane which bisects my problem into 2 separate subproblems. On each of these subproblems, I have the same data. I have the same balancing condition on each of these subproblems, right? So the integral of f on this half plane and the integral of f on that half plane is still 0. And now I can continue. If you give me a point here and an S1, I'll find another bisecting hyperplane. And again, the f is balanced in these directions. If you give me a point here, I'll find another S1. So that if I intersect here, these guys are still balanced, okay? And so on. So you can just continue in this fashion hierarchically and get kind of refined, more and more refined partition of the space, okay, into pieces, where on each of these guys, my function is balanced, okay? So the intuition is that if you take this kind of procedure to the limit, you're going to get a disintegration of a measure which is balanced. Okay, well, that's the intuition. We're kind of going to more or less prove it. So the idea is that the nth step, then the measure mu, you can write this as a sum as alpha n. So you know, I look at the decision that I made. This is probably terrible notation, but anyway, I look at either the plus side or the minus side of the hyperplane that I used. And I'm going to restrict the measure onto k alpha n. So yeah, let me write this and I'll explain. Where k alpha n is just the intersection of all the half planes that I used. Right? So this, that. And anyway, the point is intersection of half planes is always convex. So at every point, this k alpha n is kind of an element of this whatever tessellation or something. Of course, we know that the integral d u alpha. Yeah, let me call all of this mu alpha n. Okay, so d mu alpha n is equal to 0 for any alpha n. Okay, that's what we have at the nth step. So what's going to happen? Each of these mu alpha n's, of course, it's going to subsequentially converge in weak star sense, weak star topology, to some measure. Okay, this is true. The point is, however, we're going to get an uncountable collection. So you can't really do all these tricks of taking some diagonalization and stuff like that. So that won't work. But what you can do is, okay, open your books on measure theory, and then if you use a theorem, this is at least how it's presented in the work of Bruno and Milman, interpreted very nicely by Alesker, indeed. You can use whatever your favorite theorem in measure theory, for instance, a Rochlin theory, together with a Martingale convergence argument. This will ensure, so let's say Rochlin theory so I don't want to spend time on the measure theoretic arguments. I don't think that's the interesting case. I want to spend time, so let me write what it ensures and then tell you what my plan is, or what I do want to spend time on. So we'll ensure that you can write mu, okay, as promised, like that. Every mu alpha is going to be supported on, obviously, the intersection of these k alpha n's. as the partition gets finer and finer. And for any test function in L1, actually in L1, you can find, actually the order of these quantifiers is important, then for any new, it's a bit misleading because usually we see 2 for all quantifiers, the order doesn't matter, but here there's something hidden. It's new almost there. So there exists a set of measured zeros, so it is important. Okay, so for new almost every alpha, indeed, we have this convergence. So phi mean alpha n will tend to phi. Actually, I think even without taking a subsequence, as n goes to infinity. Okay. In particular, for if we test what happens to our function f, obviously then this means that if you take test function equal to f, you almost all alpha, well, this thing is going to converge to the integral of f, so it's going to be 0. Right, it's 0 along the limit, so it's 0. Okay, so indeed you'll get this balancing. But what are the remaining questions? So I do want to talk about the following things. So the questions here, two questions, which I want to address. How can we ensure that K alpha are one-dimensional? I think that's an legitimate question. And second of all, what happens to the density? I mean, it's not even clear maybe that the measure has a density, but what is the density of U alpha? So after establishing that these guys are one-dimensional, what's the density on the one on the interval they're going to support? Of course, K alpha will be convex. So once you know they're 1D, it is an interval. So I think these are the interesting questions. So, okay, what about A? A is actually easy. I want to address part A. So let's assume that we have, I just need a countable sequence. So let AI be some sequence, countable sequence of all n-2 dimensional subspace, affine subspaces with rational coefficients. That is, take your two indices between 1 and n, I and j, and just look at this. These types of, of course, Qi, Qj, rational. Okay. Then it's going to be me to see that actually the limiting guy has to be one-dimensional, because if we're given how does the construction work? If we're given K alpha n, of course we set K alpha n on the next level, K alpha n plus 1, as being K alpha n intersected with H n plus 1, either plus or minus. Okay, well, to get the partition, we're going to take our nth step guy, we're going to partition it and take both of these guys as the next level, as the offspring of that partition. Okay, what is Hn plus 1? We're going to do it in this order given by our by these guys, where Hn plus 1 is exactly the bisecting hyperplane we obtained in our bisection lemma when rotating about a n plus 1, about this n-2 dimensional subspace. So I mean, you have this A, you have your subspace, affine subspace. Of course, perpendicular to it, you have an S1, okay, because this is dimension n minus 2. And then you just kind of rotate your hyperplane until you find a bisecting one, and then that's the new partition that you create. Okay, so this is the order. So this really gives me an algorithm for really constructing it. Of course, maybe I'll get stuff which is, I'm doing it in such a strange order that maybe I'll start partitioning this guy first and only then reach this part of the space, but I don't care. Why am I doing this? Because now it's easy to claim that I get a one-dimensional guy in the limit because, so for any alpha, k alpha, which is the intersection of k alpha n, is one-dimensional. Because otherwise, let's assume that the dimension was at least 2. So convex sets have integer dimension, luckily, so I don't have to think about fractals. So I have dimension 2. So this would mean that I could find a two-dimensional subspace, let's say spanned by the principal. I can find just a subspace spanned by really principal coordinates such that the projection, the dimension of this guy after projecting, so think about this, is at least 2. Okay? If you want, you could have taken, account. So how do I choose my next bisecting hyperplane? So I look at the S1 on the sphere perpendicular to this n minus 2 dimensional subspace. Okay, this is a sphere. Okay, right? And I find my theta according to this bisection method. Okay, you can take any point here. It doesn't matter. Okay, so I just apply the bisection method. I rotate, and by this trivial oddness argument, find you bisect your space into two halves, preserving the balancing condition. Sure, but I want to do it in a kind of inductive way. So I need a countable collection, let's say, for starters. And second, you could easily construct a countable sequence where this claim that you get things that are one-dimensional false, because I'll just take all my countable collection here. I'll not bisect this part of the space. So you need to do it in a kind of. So that, that's the only reason to kind of formalize it. But yeah, all of this class is probably intuitively trivial. So I'm spending time on kind of giving you the arguments. Actually, too much time. My God. Okay. So. Anyway, what I was going to say. So yeah, so you can find a projection onto one of these principal coordinates, which is at least two-dimensional. So this means it contains, well, it's two-dimensional, right? So it contains a rational point. Contains a rational point. Okay, but if it contains a rational point in its relative interior, then in its okay. Put the relative interior here. This means that X, this guy, which wasn't our collection, so I'm going to take these points that I got in the relative interior, I'm going to raise them, and this means that this guy intersects, really bisects K alpha in a non-trivial way, so strictly bisects K alpha. So this means that along my process, I would have gotten a set which is even strictly smaller than K alpha. Contradiction. Contradiction. So really what it contradicts is the fact that this guy was assumed to be at least two-dimensional. No, so it's one-dimensional. Of course, or zero-dimensional, we could just get something trivial. So yeah, okay. Sorry, greater or equal to one-dimensional. We could get points too. Okay, so good. This addresses part A. Okay, what about part B? It's very, very simple, and yet hope by now you've convinced that it's very powerful. Okay, so what about part B? So the claim is, for part B, actually, you know, about the density. So we gave really a Riemannian geometry argument before with Jacobian and so on. I think it's great. But here, this is going to be just by hand, really a geometric reason using Minkowski theory. So claim is that if you have not like a decreasing sequence of convex sets, let's assume they're compact. It really doesn't matter, just for, if you want to really give a rigorous proof of the compactness helps, I don't know if I really want to. Anyway, compact convex sets, that's important. The convexity is important, which converge to a one-dimensional interval. So if they were compact, this guy is going to be compact. Then, if I take my measure, so remember the measure had continuous density. Take these guys. This will, of course, not surprisingly, subsequentially weak star converge to limiting measure, which is supported, of course, on L, such that the density, okay, well, I'm just repeating what I wrote before. So Z is just a normalization factor, okay, and the point is that JT is concave. Okay, and why is that? It's concave on its support. So why is that? Really, the argument is Bruno's concavity principle. Okay, so what I can do it here. So recall Bruno's concavity principle, which he actually formulated in the 19th century. States the following: if you have a set, convex set in R, let me go to n plus 1, if you don't mind, convex. Oh, and by the way, another reason, coming from convexity, there's no way that I'll use K ever for CDKN. So really, that's the second reason I forgot to mention why I use rho and not K. So for any K which is convex, in any psi direction on the sphere, the function T goes to this volume, K intersected T psi perpendicular to the 1 over n is concave on its support. So what's going on? I have my convex set. I choose a direction, psi. Okay, I project. So what is this? Given a T, I take this n-dimensional slice of my convex set, and basically this gives me the volume. This gives me the measure of the projection onto this one-dimensional line. So I get some density, supported here, of course. I get, this is blue right now. I get some density, and if I take the density to the power of 1 over n, this guy is concave on the support. Okay, this is Bruno concavity principle. Why is that? It's very easy. We actually proved it. So the claim, this is equivalent to the Bruno-Minkowski inequality on Rn, not Rn plus 1, for convex sets. That is, for any two convex sets, for any T01, the volume of 1 minus TA plus TB to the 1 over n is bigger than usual thing. Right? We basically proved this already. In fact, many proofs if you count localization. So the claim is it's equivalent. Why is that? Just draw a picture. Okay, so let's first do left, right implies left. Okay, so let's assume that I know this thing, and I start with my k here. Right, so I have my k. Whoa. So I have my k in Rn plus 1. I have my direction psi. So I need to show it's concave. So I take 2 points. I take the slice here. Take the slice here. Let's call this guy A. The slice. So this is Rn, right? So this slice is a convex set A in Rn. This slice is a convex set called B in Rn. And the point is that the set. I'm sorry, what am I proving? I'm proving, yeah, this implies that. Okay, so if I take some t midpoint here, and I take the slice here, I would like to show that this volume to the 1 over n is concave, meaning it's bigger than the t 1 minus t convex combination. The point is that this guy contains, if I know that my original set is convex, so I know that the blue guy, so blue, volume of blue guy, which I really want, is bigger than the volume of the 1 minus t interpolation by convexity of k. So it really is going to contain this guy here. If I take the convex hull of A and B and see what I get, it's exactly 1 minus, and what I get here, this is exactly 1 minus TA plus TB. Okay, so it contains that, but this, so 1 over n is bigger than 1 over n. But this guy is exactly bigger than these two guys, giving me the concavity here. Okay? And you can run this argument exactly backwards. It's exactly the same. So this implies that, because if I want to prove a Minkowski inequality, what I'll do is I'll take my copy of R. This is Rn. I'll just stick A here at some point. Let's say the point minus 1/2. At the point plus 1/2, I'll stick the set B. So which k am I going to use this information for? I'm going to use it for the set k equals exactly the convex hull of A cross minus 1/2 union B cross plus 1/2. Okay, so if I construct this set k, it's a very strange convex hull. It's going to look much more interesting than a two-dimensional picture can portray. But anyway, I just use minus 1/2 and 1/2 to see that in the middle, the guy that I get is exactly 1/2 A plus 1/2 B. But its volume is exactly the cross-section of the k that I constructed. So by the concavity, I know that the volume of 1/2 A plus 1/2 B to the 1 over n is bigger than that. So it's just running the argument backwards. Okay, so this is equivalent to Minkowski, which we proved. So we have Bruno's concavity principle. And basically, that's it. Because how do I want to conclude, I want to prove this claim, right? I want to say that if I have a sequence of convex sets converging to L, so this is L, right? I have my kind of sequence of convex bodies, which will eventually converge to it. So I don't know, this is Km and so on, coming closer and closer. Yeah, my imagination regarding convex bodies is very limited. They always look the same, but of course, they can be some cones, some interesting stuff. But anyway, they're converging, right? So let's define the function. So you take this L. Let's take the affine span of L. So that is the one-dimensional subspace this L spans. Okay, and take T goes to indeed the volume of the cross-section of Km intersected with T plus L perp divided by the volume of the full set. Okay, and I raise this to the power that Bruno tells me I need to raise it to 1 over n minus 1. So I know that it's concave. So this function, let's call this guy gamma mt. Okay, so basically I have my set. I take my Km. I project it down. I get this. The gamma mt is the density. So this is gamma mt is the density of what I got, raised to the power of 1 over n minus 1. Okay, so I know that this gamma mt is, so gamma mt is concave. on its support. And I know this support is going to converge to my interval L. And I know by Fubini, I know that gamma m to the power of n minus 1 t dt on the support, let's say, whatever, is equal to 1. Okay, because I normalized here to get a function which integrates to 1. Okay? And now, basically, if you want to really kind of make this rigorous, it's easy because I claim that gamma m is uniformly bounded. So I want to apply Arzelà-Ascoli to gamma m and show that the density really converges to something subsequentially. Okay, so gamma m is, you can do your favorite, use your favorite compactness theorem, but let's say Arzelà-Ascoli. So gamma m is uniformly bounded. It's thanks to the concavity in this property, because if not, then let's assume that it would be growing here. Its maximum point would be growing to infinity. Well, this integral would be at least as large as this guy. Okay, thanks to the concavity. So if it were escaping to infinity, I would get Lm. The support of Lm contains some intervals. So I would get that this guy is bigger than this triangle raised to the power of n minus 1. If this guy were escaping to infinity, okay, it would contradict the fact that my density integrates to something finite. So the concavity and the finite mass assumption really ensures that my gamma m is uniformly bounded. Okay, so again, the maximum point here, m cannot escape to infinity because this would contradict that using the concavity. So it's uniformly bounded, and the same reason tells you that it's equicontinuous. Well, let's say for any compact set in the interior of L. So equicontinuous for any AB lying inside the interior of L. And really the reason is, okay, it's the same picture. So basically you have gamma m, is concave. And if I have a point which lies really inside here, this is A, then I claim that the derivative, so concave function is differential almost everywhere. I just need to control the Lipschitz constant, okay? It's going to have a left and right derivative anyway. So I know that my maximum point is bounded by M. These guys are bounded by capital M. And I know that the derivative here is the slope. Well, it's bounded from below by what happens if I take this guy. So let's say I'm epsilon inside the interior. So I have an epsilon slack here. So it's bounded by the slope of this guy. The slope of this guy is the ratio between this height and epsilon, but this height is bounded by m. So really the slope here is bounded. If I'm epsilon inside, my slope is bounded by m over epsilon. Now, draw a picture. Anyway, so I have all the conditions I need to apply Arzelà-Ascoli. I know that they're going to subsequently converge to some, indeed, density, which will still have, the concavity is just a property about 3 points. It's still going to be concave. It's still going to preserve Fubini. And you just work it out, and you get that. Okay? Then it's complete. Psi was continuous density, so basically, I just project down. This density is going to converge to what I need. I just project down, and I make sure that now all of you can just complete this thing completely rigorously if you want. Okay, so these are the two ingredients that I wanted to present. Yeah. You mean in Euclidean space?
No, actually not at all.
So what we presented yesterday. So what we presented yesterday is exactly that. The fact that localization into one-dimensional needles preserves CD rho and is exactly that.
So that means that what you presented.
So let me.
You have a generalization.
Not me, but yeah. If you want, you can call this principle as follows. Uniform measure on K was CD0n. This property that J to the 1 over n minus 1 is concave, this property is CD0n in dimension and little n equals 1. So CD0n gets preserved. This is Bruno's concavity principle for orthogonal projections. It turns out that also for any, you don't need to do orthogonal projection, you just need a needle decomposition. You just need an integrable needle decomposition. That's what we did yesterday. That's the Riemannian generalization, if you will. Generalized Hansi-Karcher. Yeah, yeah. So that's the generalization with Jacobians, not via. There's no orthogonal projection on Riemann manifold. So.
The Jacobian basically would become like that.
Yeah. Okay. So, yeah, okay, basically that's the ingredients of the proof, which I wanted to present. And you can really see the interpretation of where this, okay, yesterday this was indeed a Jacobian of some, you had some hypersurface. It was this Jacobian that gave you this CD0n. And in fact, I was planning to prove this classical Riccati equation that you have on manifolds, but I didn't have time. But here you really see by hand the geometric meaning, where it's coming from. So really the interpretation, if you will, is that you're kind of, you have, the density comes from kind of being an infinitesimal convex set. So an infinitesimal convex set is trying to converge to this one-dimensional needle, and the needle remembers its shape. So that's what really the needle is doing, right? So maybe you have a convex shape. Here's my, okay. My imagination is starting to kick in. Here's a sequence of convex sets, kind of maybe truncated cones. They're converging. The density that you're going to get in the limit is indeed t to the n. Well, the volume of this section is t to the n minus 1. So the density in the limit will be exactly t to the n minus 1 here. It will remember the fact that it came from a sequence of convex sets, of cones actually, which converged here. So you see, if you have cones converging, the density J of t is going to be equal to that. Okay, but of course your convex sets could be not exactly cones, so maybe you get something which is not affine to the n minus 1, but concave to the n minus 1. Anyway, so I think it's really nice. It gives a geometric interpretation. But notice, so first of all, you can generalize this method to spheres as well. Just because spheres are so symmetric, you could do this bisection. So really, the ingredient that really used Rn is this bisection. Okay, Bruno concavity, but we could have actually. Bruno is not what I'm worried about. I'm worried about the fact that I don't have a bisection on a manifold. A way to kind of redo this lemma. But on Sn I do, actually. If I embed Sn in Rn plus 1, I can look at big spheres instead of hyperplanes, and this is what kind of works on Sn. But this is limited. Also notice that this method is really not canonical, because I could have chosen, the order in which I order my hyperplanes, is completely arbitrary. My bisection lemma tells me that there's one bisecting, but if there are many bisecting hyperplanes, it doesn't give me any way to canonically choose one. So it's really nice and geometric, but completely non-canonical. And tomorrow we'll see a method which is much more canonical. Yeah, anyway, so just for application, okay, I mentioned some applications, but maybe I'll tell you that what Kanelovitz-Shimonovich really, was there a question? Yeah, sorry. No. Okay, hyperbolic is totally symmetric. It could work, but Hadamard manifolds, no. I mean, you could say it's diffeomorphic to Rn, but you won't get something which is geodesic, because I can pretend I have some metric on Rn. I can still cut it, using hyperplanes, but these hyperplanes are not totally geodesic submanifolds. So I'll get something, and hyperbolic, yes, there should be something. Anyway, so basically what KLS proved is it's a bit about this one-dimensional analysis. They actually really showed that in inequalities that you basically want to prove inequalities using this method. So actually the extremal case, so the extremal needles have this following structure. So it's let me call this needle n. So it's an interval n, a function to the power of n minus 1, which is not just concave, but this function is actually affine. As you expect, this would be like the analog of our model spaces from yesterday. So, what's an extremal concave function? It's an affine function, right? Because the second derivative is exactly equal to 0, so it's affine. And indeed, if you want to prove, so they showed that, for instance, if I just notation, so if I denote integral over a needle, an extremal needle, as just representing the integral over its supporting interval times f of t, the density of, let's say, mu that I had before, and this affine function. So I just want, this is just notation, okay? When I integrate over a needle, I'm inserting its density inside. Then they showed then the theorem that indeed it's enough to just check. So if your application is proving an inequality, so if for any extremal needle, you want to, you know that this guy implies. So I'm back in the business of proving inequalities, let's say. So if, let's say f and g are continuous, you can relax g to be something like lower, semi-continuous. If you know that for any one-dimensional needle you can show such a problem, then in fact it holds that for the full thing, sorry, n here, yeah. Then for the full thing, for the full n-dimensional thing, this inequality also holds. Yeah, Rn I should emphasize. Let's do Rn here. Okay, so if you look at these works that I mentioned, you'll never see, you won't see the disintegration of the measure, except maybe in the work of Milman and Alesker, because really what they're after is an application. They just want to kind of continue tracing out one sequence of converging convex sets into a needle to show that, if there is an inequality, it's going to happen there. Okay, so you won't see the disintegration, but I presented it here this way because kind of to present try to present a coherent picture. So really the extremal cases are when it's affine to the power of n minus 1. So this really facilitates the analysis, right? And for instance, they have the following theorem, which let me just tell you why convex sets come up here naturally. So this four integral formulation that we already presented is indeed is their idea, using this very nice trick of turning four integrals into two integrals, like here. So if f1 and f2 are upper, semi-continuous. So I'm just quoting from their paper, so you can really see the already the refined condition. F3, F4 is lower semi-continuous, say negative, and you have two exponents, gamma and beta. Then the following are equivalent. So first thing is that for any convex K in Rn, well, this formulation that we already saw, and I explained why this is so useful. It really covers a whole range of inequalities you might be interested in. The following are equivalent. So this is true for any convex set. Is actually equivalent, if you want to verify this, it's equivalent to verifying that for any extremal needle. So you see some already one-dimensional analysis comes into this statement. So they really identified that you don't need to look at concave functions, just affine functions. The same thing with the needle. So you just verified for needles. And really the new thing that you may notice appears here is for any convex K. So really this theorem tells you that if you want to kind of prove a property on the class of convex bodies in Rn, you just need to, if it's of this form, you just need to verify one-dimensional inequality for any type of affine function, whatever. So before that, K was fixed. How do I get this for any K? Well, certainly 1 implies 2. It's because if you give me a needle, I showed to you how I can approximate it using shrinking Ks, like truncated cones, which shrink into n. So really, 1 implies 2 just by taking your convex set, shrinking them and getting my needle, getting this kind of density. So 1 implies 2 by shrinking. Km kind of down onto this needle with the density. And 2 implies 1. Okay, this is the localization method, right? So if I know this for an extreme needle, I start with a given convex set. Okay, I start doing the bisection method. I know that it's enough to establish 2 for when I take my convex set and I intersect it. So I know that I will take my density here. So I will get mu alpha, which is of the form, the integrated function of my convex set, times this needle, this affine function, because they already did the analysis of the extremal case, times my affine function. And this is exactly where I use convexity. So you should be wondering, where do you use convexity here? There is no convexity mentioned in the localization method. It works always for any measure, for any density. The convexity lies in the fact that a needle intersected with a convex set, an extremal needle intersected with a convex set, is still an extremal needle. So K intersect extremal needle is still extremal. And that's where I use the convexity. Okay, and this is why knowing something for all extremal needles implies knowing it for all convex sets. Okay, so for instance, yeah, basically out of time, but okay, they use, so, and there's an analog for, if you like, log concave measures, which is kind of part of the theory of convexity. You can replace this with log concave measures, and the needle, the extremal needles in this case would be, what is the one-dimensional density, which is probably is going to be extremal for CD0 infinity? Just guess. So CD0 infinity. The Gaussian is for CD1 infinity would be the right answer. For CD0 infinity, it's going to be what? So what's the extremal case for log concave measures? Is log affine. Okay, so exponential of not a concave density but an affine density. That would be an exponential needle. So they have the same result for that. So for instance, you can use this to show reverse. So convex sets, just some publicity for convexity here. Convex sets, log concave measures have very nice properties. For instance, you may be kind of interested to know that for any mu, which is log concave, again, let me remind you, it means that u is of the form e to the minus vx dx, where v is convex. Okay, so for any mu log concave on Rn, and for any, let's say, d-degree polynomial of degree d, you may find it interesting to know that if you take the LQ norm of this polynomial, it's completely comparable with some constants which depend, you can write this down explicitly, which depend only on PQ and the degree of this polynomial to the LP norm of mu. This is a, let's say, probability measure. Okay, for any, so of course Jensen's inequality says that when K is smaller than P, I can increase my LP norm. But the point is, this is true for any P and Q, which Q could be greater than P. It works all the way down to even minus, that's also very useful, negative moments of the order 1 over the degree of the polynomial. So basically, this completely localizes. You just need to prove a one-dimensional inequality. Okay, so it's kind of a miracle. The point is that this is dimension independent. There's no dimension here. There's no n. I'm on Rn. This is dimension independent. This is kind of in convexity, we like dimension independent stuff. So you can imagine that's a very useful property, and it's been used for various applications. Payne and Weinberger, as I said, used it to prove this spectral gap estimate. I already showed you how to prove Poincare inequality using localization, so you know how to do that. And Kanalova-Shimonovich basically had various isoparametric estimates that you can get here, and so on. So I don't know, I guess my time is up, right? So I think I'll finish here. And the plan, yeah, thanks. Yeah, let me just say, so the plan for tomorrow is to introduce, the final thing is to introduce, this method is really particular to Rn. Now recent, tomorrow is brand new things, just from half a year ago. Over the summer, Boaz Klartag gave so this method will not generalize to manifold, but now there is an analog of this theorem on manifolds, and in fact, like from a few days ago, also there's, but I won't talk about that, just publicity, there's an analog of this theorem on CDKN spaces. CD, not CD star, not anything, not RCD, CDKN spaces, metric measure spaces. This localization, yeah.
With bisection?
Not with bisection, but with tomorrow. Tomorrow you'll know by what.